Hello, and how's everyone doing today?
Good morning. I'm good.
I kind of want
Morning.
to
Good.
say good morning, but it's not morning for a lot of you folks. It really depends on where you are. We're in all different time zones, but that's
It's
kind
a
of neat.
Truly, it's evening right here in Nigeria. It's not a morning, it's an evening.
Well, good evening to all of you.
Yeah.
Um, I
That,
tr I trust that you got the links to my response videos to your first peer teaching.
yes.
And it was really interesting watching all of them. I hope my comments are helpful. I think it's easy when you're in that kind of situation, if you're presenting a proposal that deals with climate change and there's any kind of disagreement, it's really easy to fall in the trap of immediately trying to justify climate change and, that it's warming and giving examples of, what we see in our daily environment that says climate change is happening. In that kind of situation, people already have certain opinions formed. And so you really need to go to an argument that kind of takes them away from their emotions and their opinions and go to some kind of a logical argument. And so I always like to at least start with the process of science and talking about, well, yeah, you have these two competing, I've got some scientific articles, you've got some news articles from the internet, I've got the IPCC, you've got the NIPCC, it makes it seem like there's an equivalency, like it's just your opinions versus my opinions, and we're all equal. Whereas if you focus on the process and say, look, if we're going to make decisions, we really need to think about removing bias from our process because we all have different biases based on, our interests and our experiences. So let's try and see how we can remove some of those biases. And the scientific process, it goes through this peer review thing, right? Whereas a website, a news site, there really isn't any peer review. It may be true what you find on a news site. I don't know, and you don't know a priori, but at least you know something in a journal several people have looked at and evaluated. Experts in the field, have looked at the data, et cetera, et cetera. So I tend to think it's a strong argument going in into that, talking about the process. And I think it's a big deal that, in the NIPCC, one person picks the entire reviewing team. Right there, if you've got a biased person, you're going to probably get biased results. And so at least that's one way to tackle it. In your future, you'll probably run into people as you're trying to advocate for different solutions that are going to be caught up in this other hysteria. And so it's good to learn those skills now and be thinking ahead for, how to approach it. Okay. So with that said, thanks everybody for getting your videos in. We're going to do another one very shortly, but let's get to where we kind of last left off in our talk and talking about actual climate science. And this is not what we want here. Oh, sorry. It's out of the way. Go. There we go. There we go. So we had talked last time, we're looking at alternate data sources, right? So we spent a couple lectures on the surface thermometer temperature record and how that's measured, how it's adjusted, and what the conclusions kind of were. Does anybody remember the amount of warming, the size of the anomaly since the 1800s?
1.1 degrees Celsius.
1.1 degrees Celsius. I'm going to keep drilling that into your head until it changes. And it's most likely the change number is going to be higher. But I really want you to be facile with the different numbers of these different data sets and their conclusions. Because when you go to write a proposal or write stuff, it's handy to kind of know, what what the scale is that we're talking about. And so I want you to be able to describe these data sets, what time periods are associated with them, what those conclusions are for each one. And then we're going to actually, at the end of this lecture, we'll hopefully start getting into paleoclimate and looking at how the Earth has changed before. So we've seen the surface thermometer record. We started talking about satellites and the different satellites that can track temperature. And they do it mainly by two means, either the infrared or the microwave. Infrared allows you to see surface temperatures, ocean temperatures, ocean surface temperatures. Microwave radiation allows you to actually see temperature of oxygen in the atmosphere and at different levels. And we had looked at how there's actually different frequencies of microwaves associated with the oxygen at different heights in our atmosphere. That allowed us to measure different things in the stratosphere and the troposphere. And we learned that our stratosphere is cooling, but our troposphere is getting much warmer. And we learned that satellite and surface temperatures agree. Okay. Then we started talking about sea ice and the ice record. And again, read your textbook so you know the differences between the different types of ice. But in conclusions here, we looked at a couple different regions, data sets, including that from Greenland and Antarctic. And the reason why we look at these secondary data sets is our temperature data sets are main one. But if it is getting warmer, then that would suggest other things would happen. So we go to completely independent data sets to see if those follow along with our logical predictions. If it gets warmer, ice should melt. And we're witnessing that it's getting warmer in the northern hemisphere than it is in the southern hemisphere. So we would expect northern hemisphere ice to melt faster than southern hemisphere ice. And that's indeed exactly what we see. So whether you're looking at Antarctic, which is going down quite a bit, or Greenland, which is going down quite a bit, 271 gigatons per year. And so, and even the Arctic sea ice is going down. So they're looking at minimum coverage in this data set. So during the warmest periods of the year and tracing that, and you can see there's a downward trend. And I had mentioned before that our daily sea surface temperatures you can measure with satellites, and we saw the trends over the years for that. So if the surface of the sea is getting warmer and the world is getting warmer, we might actually imagine that the ocean itself gets warmer as well. But there's a big difference between the surface layer of the ocean and then the depths of the ocean. So the surface will tend to get a lot warmer, and it'll take a while through diffusion and mixing for those warmer temperatures to go further down. And indeed, just with ocean temperatures, you know, if we look at this data here, the amount of degrees, this isn't 1.1 degree differences yet, right? If you look at these average, this might be considered an outlier right now. That's because water tends to warm much slower than other things, land, materials, concrete, because it has a high specific heat. Water molecules have lots of hydrogen bonds, between 2 to 3 per molecule, while they're in liquid water. And to increase that temperature by 1 degree, you have to put in a lot of heat to start breaking some of those hydrogen bonds. But even with that said, one would think that the ocean depths should also warm as well. So here we're looking at bulk ocean temperature, and this is usually measured by drifters. These are thermometers placed in a particular place in the ocean. Then they descend to a predefined depth, and then they start recording a time series of water temperature while they move with the ocean currents. And we've got about 3,000 drifters in operation. They have radio frequency communication, so they're communicating in real time what temperatures they're measuring. And here's kind of a map from the deep ocean observing platform. And you can see there's sensors placed all around the globe in oceans all over the place, including on the sea floor. Now, other measurements are also made by ships. They'll be sailing over the water, they'll stop, they'll drop down a sensor to a specific depth and take measurements as well. And so what do they find? As you might expect, things are warmer at the top, and warmer at the top and cooler at the bottom. And if you average these temperatures, and again, we're going to look at an anomaly. So we take a time period. Can anybody tell by looking at this graph what the reference period is? Remember, for anomalies, we have to take a reference period. Usually about how long is the reference period?
30 years. So I'm assuming from 1990. Well, not 1990. Well, yeah, 1990. Until today.
That's not our reference period, no. So think about what they do for how the anomalies are calculated. So they select a reference temperature or reference period. They figure out the average temperature during that period. They get a number, a temperature. And now for all the other times, they subtract that number. So what number should you get during the reference period? So like, say in our reference period, whatever it is, the average temperature is 21 degrees Celsius, okay? And so now to calculate our anomalies, every single temperature we have in the record, we're going to subtract 21 degrees from, okay? So when we get to the temperatures in our reference period that average 21, and we subtract 21, what do you get? What's 21 minus 21?
There's no difference.
It'd be 0, right? So now look on your left scale here on your y-axis. So this is 0 difference. And so if you go along here, there should be a period by which your reference number that you're subtracting, the average value from that reference period, during that reference period, if it was averaging 21 and you're subtracting 21 during the reference period, the anomaly should be at 0. Before the reference period, it would be lower if we're in a warming world, and past the reference period, it would be higher if we're in a warming world. If we were in a cooling world, it would be higher before the reference temperature and lower after the reference period. So just by looking at this map, what's our reference time period here?
It will be 1940 to 1980.
Yeah, somewhere in this region over here. Actually, it was probably likely 1951 to 1980 used, because that's a common thing. But if you look, so let's look back at our initial temperature record. Do I have that? Yeah, here. What did we say our reference time period was supposed to be for the surface thermometer record? Actually printed on the slide, right? So look at the anomaly during that reference period. It averages out to be about 0. By definition, you've defined that reference period is going to be our 0 average. Okay, so you can always tell your reference period by looking at your anomaly data. It's the area where you're at 0 and the length that you're at 0. And so you can usually tell how good your reference is. If during that reference period, you're seeing it's not flat at 0, that means during your reference period, you were seeing change. Even though you've come up with an average number, some dates would be below the average, other dates would be above. And so if you see a trend, you know, if it's warming, you may not be able to find a time period that doesn't have a trend. But these measurements during this region seem to have very little trend during that time. So we're back to ocean temperatures. The bulk ocean temperature, and we're back to here. So you can tell the reference period is where it's around 0 for a period of time. Do you see a trend here on this overall long map? Would you agree that there's a trend in the bulk ocean temperature?
Yes, there is a trend.
Yes, Prof.
Okay. And since the 1800s, about what size of anomaly do you see between then and now? By looking at this graph.
About a nearly 1 degree Celsius, about 0.8.
Yeah, I'd say probably about 0.8. So, you know, what we're measuring. So this part in gray here, that's the range that we see. This is just the average, because back in the 1850s, their measurements of bulk ocean temperature are a lot more spotty. But if you go from there to about where we're seeing the highest, that's only about around 0.8, from minus 0.4 to plus 0.4. And so as we would have expected, since water doesn't warm as fast, the temperature anomaly isn't the 1.1 Celsius that we might have thought of previously. Okay, so let's now think again about, if we say the ocean is getting warmer, then what things logically come of that we can then use as another independent data set to even confirm that the ocean is getting warmer and that we're seeing this warming trend on the planet.
You maybe use the sea level data set.
There you go. There you go. If the ocean is warming, the one thing we would expect is that it would start to expand. When you heat anything, it starts to expand because molecules have more kinetic energy. They move further apart. That's the same is true with water when you increase the temperature. Question, Keldrin?
Yes, I thought the sea level data set would be kind of more correlated with the ice.
So the warming, would that make the sea level go up or down when you warm? If it expands?
Well, it will go up, but
right.
I was
Okay. And
Yes,
you're absolutely right that if ice is melting into the ocean, if land ice is melting into the ocean, you would also see a sea level rise. Absolutely. So both of those things are contributing in the same direction, right? We observed with Greenland about 271 gigatons per year of ice melting, and now Greenland, this is ice on land, so it flows into the water, right? Same thing with the Arctic, 147 gigatons a year, again, flowing into the water. We don't count icebergs because water levels don't change when you melt floating ice. We all know that, right? We're all good on that one. Okay. It's because ice is less dense because the molecules had to move further apart to form the ice lattice. So what are our measurements for sea level rise? So people have been using tide gauges since the 1800s. And a tide gauge, usually you have some kind of a structure that has some kind of thing sticking into the water that can let water flow into it. This water will find its level with the rest of the ocean, but you don't have to worry about the waves constantly going up and down. If this thing is tall enough to be above the waves, it'll just rise to the, an independent average level. And so that can be measured with a little scale. Okay. You could just use a permanently affixed ruler that's in the ocean, close to land, that's affixed to land, so it's not bobbing up and down. It's a little bit harder to use it because you got to worry about the waves, right? When is this ocean really flat? But if you can provide a breakwater around it, you can probably get some flatline temperature, flatline measurements. The second way we measure sea level rise, this is a more modern way, is by using satellite altimeters. And this we have data from the 1990s and beyond. And for these satellite altimeters, so like Jason 1 is a satellite that's used. It's about 1,300 kilometers high up in orbit. And it's mapping the oceans like constantly and gets a new map every 10 days. GPS satellites are used to track its precise location, so we know exactly where it is, and then it will send signals using lasers down on the ocean floor and radar signals to measure the sea level height, the wave height, and even the surface wind speed, because you can see the waves and how fast they're moving, etc. Ground stations are also using lasers to measure the precise location of the satellite, so all the measurements you're getting off the satellite are highly accurate. Okay, so again, what's nice about this data set is it's another independent data set, independent of our ice measurements, independent of our thermometer records, all of that. And so what do we see with sea level rise? Kind of what you would predict. Now in this is published data. I should have the reference, the citation for it. Where is the reference period that's being used for this data?
I'm seeing this between 1880 and
right over here. Wherever you're at 0
1895
in your anomalies, that's going to be your reference period. So they're using a reference period when the accuracy, might be in some doubt, right? But in either case, even if that's the case, whatever number they're subtracting evenly, would you say that you see a trend here?
Yeah, there's a definite trend here.
Yes, there is a trend.
Yeah. Even if you're taking from the high point to the low point, you're still going to see a trend. And now our satellite measurements, which come in about 1990 and beyond, also kind of show that similar trend. Now, here's another data set for global sea level change. And this one, they're using that, it looks to be around 2000 as their reference period to calculate this anomaly. But in either case, you still see a trend. And this is the one I think that was used in the IPCC. And so what they're finding is since 2000, about 60 millimeters, so about 6 centimeter rise. And since the 1800s, about 21 centimeters. That might not seem a lot, but over time, these things get additive. And, one can wonder if this is going to remain linear over time. So we have a lot of stuff. We've got a thermometer record, a satellite record, ice record, bulk ocean temperature record, and a sea level record. They all have different data you should be familiar with. So you should kind of know these numbers. This should be about 0.6 to 0.8, depending. And so these are a lot of the numbers that we'll be working with. There are five different independent data sets that all suggest things are getting warmer. That's what led the IPCC to conclude that the warming of the climate is unequivocal, meaning it's not really up for debate. It's pretty much undeniable that we're seeing warming here. And, I challenge anyone after seeing all this to really believe that it's not. Okay. But some people will argue, well, yeah, but climate has always changed, right? Climate has always been changing. So what? So what does that mean? And people will talk about changes in the Earth's orbit and, all different things. And so a valid question to ask is, okay, if the climate is changing now, has it changed in the past? Was it a significant change, or is just this part of a pattern that has been going on for a long time? Okay. And so scientists have to come up with ways that you can actually figure out what the weather was a long time ago, right? You can't take a thermometer now, and there's nothing you can do with a thermometer now that tells you what the temperature was 10 days ago or 1,000 years ago, right? Not really going to happen. So we need to figure out some kind of way to figure out the climate of the past. And for that, we use something what we call paleoproxies. Paleo means the past, right? Paleolithic is in past times, like archaeological stuff. And so paleoproxies are things that are indicators of what the temperature or the climate may have been. Okay. And there's a couple paleoproxies that are used a lot. First one are ice cores. Okay. An ice core is obtained by drilling into a glacier or an ice sheet. They usually have a drill like this thing here, and it starts going through into this ice sheet. And, again, I want you to read on chapter 2 about ice. There's different kinds of ice. There's 1-year ice, which is ice that is at the top. It might melt, and then more snow comes down and packs down, and you get more ice over the course of the year. But as you go lower, 2nd-year ice, 3rd-year ice, you start to get to ice that never, if you're in a cold enough area, like say, for example, Greenland or the Antarctic, you get to ice that once it was formed, it got packed by snow and it hasn't melted since it was frozen. And so that's why you've got, ice sheets that can be, thousands of meters deep, right? And so use one of these machines to start drilling down for an ice core, okay? And scientists can use the depth to estimate how long ago the ice was formed. And so you can go back pretty far, depending on the ice that you're using. Just how long ago did that ice form, okay? And then what they can do, so they drill in here, they pull out an ice core, okay? And here's a cute looking ice core. They bring it to a facility. And at the facility, they'll shave off a piece of the ice at a particular depth. So they measure along here. That's why they got this ruler here. The deeper you go, the further back in time you go. They'll cut off a slice, and in those slices, you'll see little frozen bubbles, right? That's the atmosphere at that time that was trapped in the ice when that ice formed. And so, what's cool about that is then they can now look at the chemical composition of the atmosphere that was trapped. They can measure the amount of CO2 and they can carbon date it as well. So you can actually get another more accurate estimation of what time period that gas was trapped there. Most of the ice cores that we use in climate science are from, some places that have been packed in ice for a long time. Antarctica and Greenland are the two biggest places. Greenland ice cores, you can go back about 130,000 years. Antarctic ice cores, you can go about 800,000 years. If you want to go further back than that, you're going to actually have to go down on ocean sediments and start burrowing in the ocean and digging up stuff from long ago. Turns out there's a lot of chemical reactions that happen in the air with oxygen, carbon dioxide, and they create certain compounds that then go into the seas and then fall to the bottom of the seas and get packed down. And so if you dig deep enough and pull those out by analyzing the chemical composition, you can tell something about the chemistry going on at the time. People also look at tree rings as paleoproxies. The size of the thickness of the ring tells you a lot about that particular year for that tree. And so we've got, you can use tree rings to go back about 1,000 years. Some trees are maybe as old as 3,000 years. But typical that usually we don't like to cut down those trees that have been around that long because we figure they made it this far. Let them keep going. And then you can even look at stalagmites and use isotope data. So there's a lot of different types of paleoproxies. And so let me tell you a little bit about what we've learned from these paleoproxies. First, we can tell that liquid water has been on the planet since probably its beginning. We've had lots and lots of liquid water for a while. Let's see. We can also tell that we've gone through periods where much of the water was frozen and much of it were other periods where a lot less of the ice was frozen. Okay. There was some point about 300 million years ago, we call the ice house period, where things were really, really, really frozen over. Go back about 1 billion years, there's a time where we have what we consider snowball Earth, where Earth was just really frozen very, very much. But probably more stuff from our ice core data. Okay. And this is what we can calculate, what we can at least guesstimate in terms of temperature, going back at least 70 million years. This is our temperature today. And then these are the temperatures as you go back. These are tens of millions of years. Notice there does seem to be a big blip. We're going to talk about that blip a little bit later. Okay. So what do you conclude from looking at this data? What's been happening to the temperature of our planet over the last 70 million years?
It has been increasing.
Increasing? Here's our temperature, our reference period somewhere in here, right? This is the past.
Oh, yeah, it has been decreasing.
There's been a warming in that period.
Yeah, it's been cooling down a lot, right? Look how warm it was 50 to 60 million years ago. Anybody know what was going on like 60, 70 million years ago? Know anything about the planet? Then that's when the dinosaurs were running around the planet. We think the extinction of the dinosaurs was about 62 million years ago. So that's to give you kind of an idea of how long. In terms of life, complex life, multicellular life, we think have only been on the planet for about 500 million years. So not even a billion years for multicellular life, only about half that. We had dinosaurs ruling the planet from about 120 million years ago to actually probably about 200 million years ago to about 60 million years ago. But it does look, in terms of our temperature, that it's been coming down. Okay. Now, if we expand this up and we look from 50 million years ago to today, we notice that about 30 million years ago, we start getting these bigger fluctuations. You see these things here, see how it's going up and down, up and down, and up and down, and up and down, and up and down. It didn't seem to used to do that before about 30 million years ago. So these are tens of millions of years. Okay. So now if we expand this up and let's just look at this area where we've got lots of good ice core data from, and this is what the temperature anomaly looks like. Okay. Again, we're using our period as a baseline. And so what are you seeing here? What do you notice in this data? This is 400,000 years here back previous. This is our present time period. What do you see in this data?
From the previous peak that was portrayed, there is a period when the trough and amplitude, where the variation of the trough, that period where it starts to like elongate trough to peak. I think the closer we get to present, that's where there is the huge spikes of temperature changes. So like, right, yeah, here, that period. Can you go back to the slide? To the present slide? Yeah, here. So this period is the period where we see those huge spikes, and it's actually what I would call a turning point before temperature begins to rise. From before, temperature used to like, it used to be colder, right?
It used to be colder and more constant. Let's go back to the one from a long time ago, right? Yes. So this seems to be slowly getting cooler, but now over here, you can see, look how thick these lines are. That's because it's going up and down and up and down. The orange line is just the average, but the actual data is shown in blue. When you magnify that up, you can see that here. And then when you magnify that tail up, you can see in the last 30 years, or I'm sorry, 400,000 years, you start to see these kind of cyclic events. And what you're actually seeing is these are ice ages. These are what we call ice ages. And they're separated by what are called interglacials. Interglacials will last about maybe 10,000 years, and then it cools down, and then you get another ice age. So you get an interglacial, cools down, an ice age for a period of time, about 30,000 years of ice age, and then it warms up pretty fast over the course of 1 million years, or no, I'm sorry, of several thousand years, to an interglacial period. So these peaks here are what we call the interglacials. Okay. Now, these warmer interglacials, they last around 10,000 years. And if you look at the temperature rise in between an ice age and an interglacial, they're on the order of maybe 6 degrees Celsius change. So that's the difference between now and the last ice age. Okay. We had an ice age probably about 20,000 years ago. We were in an ice age. So humans were alive during the last ice age, right? We were more like cavemen then. It's before any recorded history. We only have about 5,000 years of recorded history. So now if you go back a little bit before that, we were in a big ice age, okay? Now, this is long after the dinosaurs were dead. Remember, they died 62 million years ago. Humans have only been around for about 500,000 years. So around this period of time, and we weren't really Homo sapiens until somewhere in the middle of this, okay? So we've been living through these kinds of things, although albeit as cavemen. And note that when these things change, when you go from an ice age to an interglacial, it's about a 1 degree Celsius change for about 1,600 years. Okay. Now, our temperature anomaly that we're seeing, the 1.1, what time period is that over?
It will indicate that we're in the interglacial at this moment.
Uh-huh. But in terms of our 1.1 degrees Celsius anomaly that we're talking about with climate change, over what period of time is that anomaly?
It's within the last, we want to be specific.
Remember, it goes back to the 1800s, right? So it's the last 200 years.
Yeah, 200 years.
Yeah. So a 1 degree temperature rise in 200 years versus 1 degrees over 1,600. Callisto, you had you had a question?
Yes, sir.
Yes,
So
please.
first, hello for everyone. So now I'm confusing because actually we are talking about warming in the system, in the climate system, and the previous graphic that you showed us showed almost the opposite. So I want to understand about
Okay.
it.
So
This
look at
one.
the time scale here. This is in millions of years, right? What we've been talking about with the surface thermometer record, when we talk about global warming, we've been looking about since the 1800s, okay? So we're talking about a specific time period right now where we're seeing warming, okay? That's not to say that the Earth hasn't periodically warmed and cooled over the past. There seemed to be a lot of variation over, these are tens of millions of years. This is over the last 400,000 years, okay? This is 400,000 years ago. And so this is like right between here and here, it's about the last 10,000 years. So it just warmed up. We were in an interglacial, and then it seemed to start coming down. So this is the last ice age over here, and it looks like we've had about this kind of change. Now, we're on the tail end. We should be sliding in to an ice age, okay? We should be slowly starting to go down at this point, except now we're going back up. Okay. If one, remember from our ice cores, we can also measure the chemical composition of those things. This is how CO2 levels track with our temperature calculations. So we'll get into what CO2 is and why it's important a little bit later on, but I just want to throw this out there since we're talking about ice core data. Okay, so now this is over the last 400,000 years. let's narrow our time scale even smaller, more recently in the past. And so this is the last 10,000 years. Okay. So remember on here, more than 10,000 years ago, we were cold. We were in an ice age. About 10,000 years ago, we start coming out of that ice age and we're in an interglacial for about 10,000 years. And then now we seem to start going back down. And notice, you know, this little dip point, that happened not too long ago. And we have a word for it. It's called the Little Ice Age. Okay, that was, I think, about about the year 1000, I think. So this is in medieval times. It was getting colder and colder, and we had what was then known as the Little Ice Age, or what we now call, what historians have been calling the Little Ice Age. And then temperature started to pick up. Okay. So a couple conclusions to draw from this. Okay. Paleoproxies tell us that we've had liquid water on the planet for a long time, and climate has varied widely over Earth's history. Okay. There were times the Earth was covered in ice, and we were in ice ages, and times without. Okay. The last 30 million years have been a lot more variation, where we start to see these alternating glacial ice ages and interglacial periods that seem to have been alternating. And at least looking at our cyclical variations, it looks like we're at the point of the cycle where the Earth will begin cooling and dropping down into a little a slow decline. Remember, these declines take thousands of years, right? We saw that the temperature change that we were seeing in these things were about 6 degrees Celsius over about 8,000 years that it takes to drop. Okay, so it's about a 1 degree Celsius per every 1,600 years. So it's a slow decline, but that's what we might expect based on how we see these historical processes. Now, the other thing we can tell from the paleoproxies is that all of those changes, the widening up and down and the glaciation events, those all have to be due to natural processes and aren't due to human activity, right? Because humans weren't around for it. So it can't be due to human activity, right? And you know, when I learned about this, it was surprising to me to see. I mean, I had heard that there were ice ages in the past, but I wasn't really sure on the specifics and how long they lasted, how often we had them, and the fact that there's a cyclical pattern to it. Now, the interesting part is we're on the cyclical pattern that should be bringing us down. Except now we're going up, and we're going up way faster than we've ever gone up out when an ice age has ended and we've gone to an interglacial period. That would usually take 1,600 years to go up a degree. And now we're going up in more than a degree in just 200 years. So if we took that rate of change as constant, that would mean over 1,000 years, we would be going up, you know, close to 5 degrees, 5.56 degrees in just 1,000 years. So the rate of change now is a lot different than we've ever seen in our Earth's history. And we're in an odd part of the cycle for the temperature to be going up. So I want to give you a couple moments to chaw on that, right? Because, you know, all we're expecting in this course is to see everything's getting warmer, everything's getting warmer. But as a scientist, we can't ignore data. We got to look at what the data says and try and come up with what does it all mean.
Could you go back to that last graph?
Sure, sure. Hold on a second. This one here.
Before that.
Okay, so this is the last 10,000 years. So this is the last 400,000 years. This is
Yeah.
looking at both CO2 and temperature, but the temperature's in blue.
Okay, looking at the temperature for the tail end of the graph, as opposed to the entire graph with the ice ages or going into the ice age period, it's a lot more linear as opposed to the tail end of what it is now. Although it is decreasing, kind of indicating that we are going into ice ages kind of steadily, it's steadily at the top, right? It's going down at a far slower rate into it where we're going into a far slower rate of an ice age as opposed to earlier trends. So like, that was kind of something that caught my eye as well.
And that's a good observation. And that, again, let's expand this tail end over here. So we're just going to look at, from 0 to 10. So just this part here. So kind of at the top and forward, that's what this looks like. Okay. So about 10,000 years ago, we're coming out of the ice age. This is the interglacial period that humans have been existing for the last recorded history. Egypt, the Roman Empire, all of that during this time. And then temperature seems to start coming down. And now we have this spike. This spike is present day. This is where we're at now. And it doesn't show, don't think that you can't see that the spike is coming back down. It's just going up. And that's where we're ending right now, is we're ending right at the top of this over here. So does our temperature change that we're experiencing now, does it fit the model? One, it's going in a different direction, although you can say, well, there was a lot of noise. Like if you look in this, there's noise in this kind of data over here. There are some spikes. Maybe we're finishing off the spike, but the rate of change due to natural processes that we've seen in past before humans was about a degree every 1,600 years. We're seeing a far faster rate of change, which seems to suggest something's going on. Like if you're standing by a river and you see the water flowing by, 4 miles an hour, 5 miles an hour, and your kids are playing on the water and swimming in it. And then all of a sudden, the water starts streaming down at 20 miles an hour. You might conclude that something has changed. Because why all of a sudden is the water moving way faster? Something has done something. We're not saying what yet. We haven't tried to attribute what's going on, but we're just looking at what our climate records tell us now, what they tell us about a long time ago, and then we'll try and what we're going to get into next week is actually the physics of warming and the physics of planets, and when you shine sun on them, what do they do? So we can actually talk about, and this will lead us into actual what climate models are and all that kind of stuff. So we'll get into the actual physics of it next week. Any other questions? Thanks, everybody. I'll try and have this video up as soon as I can, and send links out to it for people to rewatch. And I'll be setting up the next Flipgrid soon. I just gotta settle on the question. The question is most likely going to be, over this last week's material, which is, tell me about our changing climate. What is the evidence of global warming? What supports it? It'll be broad like that, and then you can talk about the different things we've talked about over the year. Imagine that you're trying to teach somebody that's new to the class, about the global temperature record and all the data that we have about global warming, or you're trying to teach somebody who doesn't really know much about global warming what it is we observe. Let's not talk about what caused it. Let's just talk about this is the data that the evidence for global warming. And I'll post that peer review question shortly on Flipgrid, and I'll send it out. Thanks, everyone. Have a great day.
Thank you.
Thank you so much, Prof.
Evening.
Thank you so much, Prof.
Okay, bye-bye.